Hi, good afternoon, everybody. My name's Rod Giles. I'm the head of CAD and CAE at Royal Enfield. And I have got a short presentation regarding using our advanced simulation tools at Royal Enfield. Royal Enfield's the world's oldest continuously manufacturing motorcycle company. And we are based in Chennai in India, with a UK technical centre in Bruntingthorpe in Leicester. And of course, I'm working from home at the moment. We make a number of motorcycles in the category of 250 to 750cc motorbikes. And the motorcycle that you see behind me is our Interceptor model, which is the UK's best-selling motorcycle in its class, and has been very successful for us. We've recently launched a new model in the Indian market called the Meteor, which is a 350cc single cylinder engined model. So I've got two topics to talk about today regarding using automation. One is a project that we have done to look at the automation of the gearbox analysis, and that work has been carried out by Nihit. And then the second topic I have is using iSight to look at some acoustic performance of our exhaust systems, and that work has been carried out by Nabil, who some of you might remember gave a very successful presentation at last year's last conference. Okay, and the picture you see at the bottom is the side view of our new Meteor motorcycle. Please look it up on the web, it's getting great reviews. So, first topic is exhaust system, is a gearbox system, and we've got a couple of applications that we've developed leading on from the work that we did in partnership with TECHNIA some years ago now, looking at automating repetitive tasks in a gearbox. And this is very important because we have anything from 1 to 6 gears in a gearbox. There's many iterations in the design process, and also there are many couplings and contacts within the gear pairs, and so they cannot be analysed separately. We have to analyse the assembly. And so this leads to a very large number of possibilities for gear position and gear configuration, which means that there are a very large number of analysis runs to run. So the first tool that's been developed is a tool to prepare the gear shaft. So the gears that are used in the gearbox are lying on this shaft, and some of them are fixed and some of them can actually move position, hence their splines. And we can use this dialog box to import the geometry, identify which regions on the shaft have gears attached to it, and also where the bearings on the shaft are. So in this case, the bearings would be at the ends of the shaft. And then also we have a dialog box for to apply the torque requirements for each gear. So we can actually carry out a run for all the torque applied for each gear as a separate load case. So that's how the dialog box looks. There's other options. We can look at the number of gears that the gearbox might have, if it's a 4, 5 or 6 speed gearbox, and so on. The second dialog box that we have a custom UI for is a gear pair analysis. Although it's a gear pair, we actually have 3 gears. So we have the gear pair in contact in mesh themselves, and then there's a third gear that's in front of the larger gear behind it, and this gear actually drives the intermediate gear by a series of lugs, or called dogs in the UK, pushing against the openings in the other gear. So we need to look at the stresses not only in the gear tooth, but also in the gear wheel as well. So this dialog box looks at individual gear pairs and can completely automate the setting up of the model and applying all of the loads, constraints, boundary conditions, and so on. And this is what happens when the shaft dialog box has done its work. So we can see we have a shaft which has got some regions defined on it for bearings. We've got a continuing coupling constraint to a reference point that we constrain. So we constrain the shaft in the correct way, and then all of the gears are also similarly apply a load through the coupling constraint to the splines on the shaft. And this is now completely automated, so we just need to bring the shaft in, fill in the dialog box, and the output is the ODB. And then we also have another application that reads an ODB and creates a report file. And so this is just a single slide from that report. So it's an automated report where we can show for each gear where the particular high stress concentrations are in the shaft, and display that in a report. And then once we have done that, we have another application which can take the data from the ODB and run through FE-Safe to do a durability assessment. So this is a description of the FE-Safe process. We are using a script written in Python that generates the LDF that's required for the FE-Safe, and then it can run, FE-Safe can run in an automated fashion to produce an ODB which contains the durability data. And in this case, the user can input data in terms of what the primary gear ratio is, so i.e. what speed the gearbox is running at, the expected variation in load, and that can vary between model. It can also vary between rider. Some riders are more aggressive than others, and then where the ODB is residing for the stress results. And we use Excel. We can read an Excel sheet that contains the durability cycles. Okay, so that was a gearbox durability analysis. And then the second item I have is iSight using acoustic simulation. And what we are looking at here is carrying out a parametric optimization study to try to improve the transmission loss in the exhaust system. So we have an exhaust system here on the top left, and we can carry out a acoustic analysis using some acoustic software that we have to produce the transmission loss curves that you see on the top right. But what we'd like to do is to be able to obviously optimize this design, and what Nabil has done is to look at just a couple of parameters to start with, and that is that looking at the perforations in the muffler, inside the muffler, which we know from previous experience have quite a big impact on the sound performance. So you can see here that we've got a series of holes inside the muffler in the tubes, and we can vary both the diameter of those holes and the pitch spacing of the holes, and completely automatically find the transmission loss for those parametric models. And we need to describe a target function, and what we want to do is to minimize the area between the transmission loss curve and a target function. And if we can do that and raise up the level of the transmission loss, we will have a quieter exhaust system. So this is some of the output from a DOE experiment, and then looking at the response surface. And we have radius and spacing for our perforations, and then the objective function is plotted on the z-axis, which is the area. So the target is that we want to minimize the area, and looking at this map here, we can see that the optimum must be somewhere within the dark blue area. We also can produce sensitivity plots to see which is the more sensitive radius or spacing. And then we went on to do an optimization so that we can see the change in the hole size and hole pitch. And you can see that after a certain number of iterations, the optimization settles down, and pitch and hole size both increase gradually to get the optimum solution for the transmission loss. And we can see this is a result of that work, where we've raised in some places, we've been able to raise, just by looking at optimization, the transmission loss by perhaps up to 5 dB in certain areas. And then we can use that to, so what we want to do in future is to adjust our target curve to give us the character of the noise, rather than just looking for an overall noise quietening. Okay, so I'd just like to, in summary, explain the relationship between Royal Enfield and using SIMULIA software with our partnership with TECHNIA. We've had a very good relationship with TECHNIA for a number of years, and we've built up a absolutely superb library of automation tasks, and these two examples are areas where we have developed leading on from the work that was carried out with TECHNIA. And the second thing that we have found working from this is responsiveness, so that any issues that we have, or anything that we have a question about, we get a very quick response and very detailed, have a very good understanding of engineering and the concerns, which leads me on to the third point. We can be sure that we are talking to engineers with a very good grasp of the not only the software, but also an understanding of the engineering background into and why we're trying to do what we're trying to do. So with that, I would like to say thank you very much for giving me the opportunity for talking at this year's conference. Thank you.